Hello, class. Welcome to the Stat 211 lecture on chapters 2.3, 2.4, and 2.5, displaying and describing data. In this lecture, we are going to talk about the shapes of distributions, measures of center, and measures of spread. Let's get started. So let's look at Objective 1, Shapes of Distributions. In our previous lectures, we have talked about different graphical displays. One of the most important of these displays in statistics is the histogram. We often use a histogram to determine the distribution shape of a data set. When we are looking at something that is a more complicated data set with multiple variables, usually the variable of interest, our response variable, is the one we look at as for a histogram. So being able to identify the shapes of histograms is extremely important in this class. Specifically, we generally like to be able to determine if a histogram is unimodal and symmetric. So that's really going to be our focus here. A histogram is symmetric if its right half is a mirror image of its left half. Very few histograms are perfectly symmetric, but many of them are approximately symmetric. So if we take a look at this histogram, notice that it is not perfectly symmetric, but it is approximately symmetric. In general, in statistics, we look for histograms that are approximately symmetric, and then we still generally just abbreviately call them symmetric. What it looks like when a histogram is not symmetric is when they are skewed either to the right or to the left. A histogram with a long right hand tailed is said to be skewed to the right or positively skewed. A histogram with a long left hand tail is said to be skewed to the left or negatively skewed. The way I like to remember it is the word skewed kind of sounds like the word ski. So skew right, ski right. Skewed left, ski left. To demonstrate that, if I were to have a little person on top of a mountain and they were going skiing, and we start skiing at the top of the mountain, we would go down this way. We are going to the right. Skewed right, ski right. Same thing for skewed left. At the top of the mountain, we put a person, little skis on. What direction are they going to be skiing down? They're going to be going this way. So ski to the left. Just a little trick to help you remember all this. As I mentioned before, there were two main things we look at in terms of histogram, whether they are symmetric or not, and then their modes. We know what modes are from a mathematical standpoint. You know they are the numbers that occur the most. Graphically, though, they are a high peak or high point of a histogram. A histogram is unimodal if it has only one mode or one high peak, and bimodal if it has two clearly distinct modes. So the graph on the left is an example of something that is unimodal. On the right, bimodal, two high peaks. Of course, peaks aren't always there, and in that case, we call that a uniform histogram. So a histogram that does not appear to have any mode and in which all the bars are approximately the same height is considered to be a uniform histogram. And what would be talking about statistics if we don't address the outlier in the room? Outliers are data that stand away from the body of the distribution. Outliers can affect overall analysis results, so their identification is extremely important. To have an idea of what a outlier looks like graphically, we have this graph below. Notice that most of the distribution is located from that 3 plus, but we have couple points or one single bar away from that rest of the distribution. We would identify that as an outlier. Outliers are a pretty important topic in statistics, and we'll definitely address outliers more, how they happen, why, things like that, more detailed later. But for today, it is just important to be able to identify them graphically on a histogram. So, because we've learned all these new vocabulary, it is pretty important that we can make sure we can use them. So, taking a look at this histogram, first thing to understand is this histogram symmetric or skewed? Well, to me, right off the bat, it doesn't look symmetric. It's not even close to a relatively mirror image. So, pretty easily, this is going to be a skewed image. Specifically, we are skewed right. We are skiing to the right. Also, since there seems to only be one mountain, that tells me that this is going to be unimodal. So we've got a skewed right distribution that is unimodal. This brings us to our second objective, talking about measures of center and then finally of spread. Some of these, and hopefully a lot of these, measures of center are familiar to you. In statistics, a measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within the set of data. Colloquially, measures of central tendency are often called averages. This is generally a place of confusion for some students in this class because we've been trained so hard when we hear the word average to automatically think of a sample mean. But that's actually not always the case. I want you to think about the scenario of Texas for a moment. So imagine people are trying to grow very nice green grass in Texas. And one neighbor looks at a company who is fertilizing some grass and putting grass seed, and he asks the lawn taker what type of lawn seed most people have. And he responds, on average, people have a seed type. Now, when he used the word average, he wasn't referring to a sample mean. He was actually referring to the mode. What type of seed does or do most people have? So be careful when you see the term averages that you're not only thinking of the sample mean. It could be the sample mode. It could possibly be the sample median. Context matters. So speaking of mean, median, and mode, let's talk more in-depthly about those measures of central tendency. So suppose observations in a sample are x1, x2, all the way to xn. We denote the sample mean with a lowercase letter x or some other letter with a bar over it. So to calculate the sample mean, we say x bar equals the summation of xi over n. Expanded, that is x1 plus x2 plus dot 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 all the way to plus xn, all divided by n. So this slide is pretty important to us because it's introducing a whole bunch of notation that we might be unfamiliar with. So starting with the summation. So this is the Greek letter epsilon, and in calculus, this means to sum, which basically just means add. So anytime you see this symbol, it means summation, and it means we're just going to add all the terms. When we are trying to denote a sample size of unknown length, we generally denote it as so, where we'll just have a variable with a subscript, where that subscript denotes the placement. So like x1 is the first observation in the data set. And we go x2, that's the second one, dot, 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 for however many are in the set. And we end with xn. N denotes our sample size. That is the number of observations in our sample. In statistics, N is pretty universally used to represent the sample size. Sort of like X and Y's are usually used to denote the sample variable. So like a sample of X's. N is sample size. And so using a subscript of n is just saying, it's the last observation in however long our sample size. We still calculate the sample mean the same way you've learned since you were in early elementary school. What is different in this for you is the notation, which I'm trying to get you a little more comfortable with. You will see xi used to denote an observation in our data set, but it's kind of that generic a variable. So we're adding all of them up. Let's take a look at an example. Suppose you have 5 quizzes in your biology class, and the scores were 78, 83, 92, 68, and 85. Find the mean score. So using our notation, x bar equals the summation of xi over n. If I were to identify each of these variables with that x notation, this would be x1, x2, x3, x4, and x5. This is useful because this is an easy way to see that there are 5 observations in our data set. Now to find the sample mean, we add each of these 5 observations together. 78 plus 83 plus 92 plus 68 plus 85, all divided by our sample size of 5, equals 406 divided by 5, and we simplify that to 81.2. So our mean score of our 5 quizzes is 81.2. Now we can talk about the median. Another measure of center splits the data set in half. Given that the observations of a sample are x1, x2, all the way to xn, and those data sets are arranged in increasing order, the sample mean is denoted as followed. So in statistics, we denote the sample mean with a lowercase letter, usually an x, with a tilde over it. So again, this represents the sample median. Now, if you recall how you've spent your life finding the median previously, usually what you do is you arrange your data set in order from least to greatest, and you cross out until you get your center value. That is still true. That method still applies. But again, we're still trying to teach you some new notation here. So in the case where we have a odd sample size, like 5, the position of the median is x, and then subscript n plus 1, close parentheses, divided by 2. So if we have a sample size that is 5, its placement, 5 plus 1 divided by 2. 5 plus 1 is 6, divided by 2 is 3. So that means x3, position-wise, is our median. Again, this is just using the notation, but generally the process that you've always done to find the median is still applicable. To be honest, I won't know which method you choose. I'm just giving you your options. If n is even, then you would take the two center positions and find the average of those two positions. Same as you've always done. Let's take a look at an example. So suppose we wish to find the median of 78, 83, 92, 68, and 85. First step, arrange the data values in increasing order. So 68, 78, 83, 85, and 92. Determine the number of data values. There are 5 data values, so n is odd. Since n is odd, we just know that the median is the middle number, so 83. When we have an even number, let's make sure we know how to do that as well. So suppose we want to find the median of 20, 15, 12, 27, 13, 19, 13, and 21. Again, first things first, arrange that data in increasing order. So this becomes 12, 13, 13, 15, 19, 20, 21, and 27. Determine the number of data values. There are 8 data values, so n is even. Because n is even, the median is the average of the two middle numbers. So for us, middle numbers, so cross off, cross off, cross off, cross off. Two middle numbers is 15 and 19, so find the average of the two. 15 plus 19 divided by 2 equals 17. So our median is 17. Circling back to how this relates to our previous distribution discussion is really pretty simple. When the distribution of values for a variable is symmetric, we will find that the mean and median are equal. However, if we have a skewed distribution, our mean and our median are not going to be equal. Because of how you calculate a mean, the mean gets dragged towards more extreme values. So the mean is always going to get pulled to the tail. So in this case, when it is a skewed right distribution, the mean is going to be larger. If we were dealing with a skewed left distribution, again, the mean gets pulled to those more extreme values, meaning the more unusual ones, but the median is going to stay closer to our mode, closer to the peak. So in that case, the median would be larger when we're at a skewed left distribution. This brings us to talking about measures of spread. So generally in statistics, when we are thinking about distributions, we have the distribution itself that we need to look at. But when we're trying to very quickly, I guess we can say, I don't want to say estimate, provide a simple summary of the data, one way we have done that traditionally is to provide a measure of center. So if you're looking for a single number to describe the data, most people use the mean or the median. What's the center number to describe the whole data set? A better alternative would be to provide two numbers. One number being the measure of center, the second being a measure of spread. So a measure of center will tell you what is the average, what is the most likely number that appears. The measure of spread will tell us how spread out our data is. So, as I said, locating the center is only part of the story. Are the data near the center or are they spread out? Is that highest value much higher than the lowest value? So a better method of understanding the data, instead of just providing a single number, a measure of spread, provide two, a measure of center and a measure of spread. So you have a better picture of the whole data set. The most common measure of spread that you are familiar with is the range, and it is the difference between the maximum and minimum values. So range equals the maximum value minus the minimum value. So pretty easy. If the ages of guests at a dinner party are 16, 18, 23, 23, 27, 35, and 74, the largest value is 74, the minimum value is 16. So the range would be 74 minus 16 equals 58. Easy. Another way we look at measures of measures of spread is looking at percentiles and quartiles. Percentiles divide the data into 100 groups. So the nth percentile in the data value such that n% of the data lies below the value. For large data sets, the median is the 50th percentile. Quartiles does kind of the same thing, only it divides the data up into quarters or 4 parts. We have quartile 1, quartile 2, quartile 3, quartile 4. So the first 25%, so from the beginning to 25% of the data in, that's the first quartile. From quartile 1 to 50%, that gives us quartile 2, which is usually the median. Then from quartile 2 to quartile 3, we have that next group of 25% of the data. And then quartile 3 to 4, we have that last 25% of the data. So the median of the lower half of the data is quartile 1. The median of the upper half of the data is quartile 3. If we're thinking in terms of quarters, this would be 25 cents or 25%, 50% or 50 cents, and quartile 3 is 75, so it's the 75th percentile. We don't always use measures of percentile and quartile to denote a measure of spread, but what we do instead is use something called the interquartile range. So the interquartile range is the difference between the upper quartile and the lower quartile. Simply put, the IQR, interquartile range, equals Q3 minus Q1. So this is still really a measure of range, but what it does is it only measures the range in the middle half of the data. So going back to this screen, the interquartile range gives us a measure of spread right here, that middle 50%. Another measure of spread is the sample variance, and then with it goes the sample standard deviation, which we'll talk immediately next. Honestly, in statistics, we use sample variance more than any other measure of spread. The sample variance is a measure of how far the values in a data set are from the mean on average. The sample variance is denoted with a lowercase letter s and an exponent of 2, so s squared. The formula is the summation of each observation in our data set minus the sample mean and quantity squared, divided by our sample size minus 1. So really, if we break this formula down, we have a average. Sample size. This is the distance away from the mean, that measure of center. Because the mean should be in the middle of the data set, numbers below the mean would be negative, where numbers above the mean would be positive. So one way we can eliminate that negative positive, which is purely directional, is to square it. Because if we square a negative number, it becomes positive. Also, by squaring it, we punish data values that are more extreme than those that are closer to our average. So something that is only 2 places away will have a distance of, or this summation of 4, but something that is 9 places away is 81. So it is a much larger number. So kind of having an understanding of how these variances are interpreted. So if your variance measure, your S square, is small, that indicates to us that we have low variance, that our data is not very spread out. Middle, moderate variance, there's a little bit of spread, but not extremely. And then the case where we have high variance, where your data is very spread out and it's not super concentrated within a short period. Let's take a look at an example to kind of put this into a little more perspective. The following table represents the average monthly temperature in degrees Fahrenheit for the cities of San Francisco and St. Louis, according to the National Weather Service. Now, if you know anything about the weather in San Francisco, you'll know that the temperatures are pretty mild and they stay pretty consistently throughout the year. And so if we even look at it from January to, which would be winter, to say July, August, the summer, you can see that that data isn't really that extreme. We go from 51 to 61, 63 in September. So this data is not as variable compared to other cities like Morgantown. Then we have St. Louis, which we can see. We can look at their winter temperatures being in the 30s as opposed to their summer temperatures, which are in the 70s, almost 80s. So there is way more variability in the temperatures in St. Louis. So what does that mean? So San Francisco has a smaller spread. The values are going to be closer to the average, and they're going to have a smaller variance. Variance measures variability. San Francisco has way more consistent temperatures. There's not a whole lot of variety in the temperatures in San Francisco as compared to St. Louis, where we've got a larger spread of numbers, which means those values are going to be further away from the mean, and we're going to have a larger variance, which makes sense. The temperature is more variable in St. Louis. I mentioned when I first said variance, I said it goes along with something called standard deviation. And here we are, standard deviation. So the units of variance are the units squared of the data. So if we are looking at our degrees in Fahrenheit, like in the previous slide, if we provide the variance, the units for that would be degrees in Fahrenheit squared. And sometimes that messes with the interpretation for people, not having the same units. So what we often do is we use the sample standard deviation instead, where the sample standard deviation is simply the square root of the variance. This means that the standard deviation is going to have the same units as our data. So we can have degrees in Fahrenheit for our averages, talking about the data, and we can still provide the standard deviation and its units will also be the same. Standard deviation is pretty easy to calculate, assuming you have the variance. It is simply the square root of the variance. It is denoted by a lowercase letter s, and again, we can find it by taking the square root of our variance. So how can you go about calculating the variance? Because doing this by hand, that's part of this. So first step, we will have me write out the formula so we can remember where we are in this process. So first things first is we calculate the sample mean. Then, for each sample value xi, so every observation in our data set, we compute the difference between our observation and the sample mean. We call this the deviation for the value xi because we're computing the distance. How far was each observation away from the mean? Kind of got into this already. So with all of those deviations, we then square them. Squaring them gives this the distance the same units in the sense of we don't have negatives and positives. They are all just plain distance away from the mean, all positive. And it shows penalties or gives penalties for data that is further away from the mean. Once we have all of our squared quantities, we add them all up. Remember, summation to add. Once we have our summation, we then divide the sum by our n minus 1. Remember, n is our sample size to obtain the sample variance. If we want to add in a step 6 to calculate the standard deviation, we can just say step 6, take the square root. Let's take a look at an example because I personally think seeing those steps are great, but I would need an example. A company that manufactures batteries is testing a new type of battery designed for laptops. They measure the lifetimes in hours of 6 batteries and the results are presented in the following table. Find the sample variance of the lifetimes. So we are given a data set of battery lifetimes of 3, 4, 6, 5, 4, and 2. Excellent. So the first thing we're going to do to calculate the sample variance is to calculate the sample mean. We know how to do that. Add up each observation in our data set and divide by our sample size. We had 1, 2, 3, 4, 5, 6 observations, so 3 plus 4 plus 6 plus 5 plus 4 plus 2, all divided by 6. This gives us a sample mean of 4. Step 2 is when we're going to calculate the deviation. So we know that our sample mean is 4. So what we're going to do is we're going to take each observation in our data set and subtract it by 4. So 3 minus 4 is negative 1. 4 minus 4 is 0. 6 minus 4 is 2. 5 minus 4 is 1. 4 minus 4 is 0. 2 minus 4 is negative 2. So we can notice that we have both positive and negative numbers. where negative numbers means that it was a observation value that was less than the mean. Numbers that are positive had observation values that were greater than the mean. Not a problem, just something to be aware of. Next step is we take each of those differences and we square them. So -1 squared is 1, 0 squared is 0, 2 squared is 4, 1 squared is 1, 0 squared is 0, -2 squared is 4. So now we have the squared deviations. Next step, add them together. So we will add our last row in our table that we're forming. So 1 plus 0 is 1, plus 4 is 5, plus 1 is 6, plus 0 is 6, plus 4 is 10. Last step is to divide by our sample size minus 1. We can remember that our sample size is 1, 2, 3, 4, 5, 6. So take our 10 from our previous slide, divide it by 6 minus 1, which would be 5. 10 divided by 5 is 2. Not bad. A lot of steps, but I don't think each step individually is that hard. To calculate that sample standard deviation, square root. Take the square root of 2. All right, question for us then. Standard deviation and histograms. Let us order these histograms below from the smallest standard deviation to the largest standard deviation. Remember, standard deviation is a measure of spread. Smaller standard deviations indicate smaller measures of spread. So, the smallest standard deviation would be C. Most of the data is clustered here. There is fewer observations away from our center. Our second largest standard deviation would be A, the uniform distribution. We have our data pretty consistently spread throughout the data set. The largest standard deviation would be B. This shows a highly variable data set. Symmetric, yes, but also highly variable, where we have multiple levels of extremes in different locations. So, to finish up this chapter, I would like to start looking at how to calculate some of these measures of center and spread in StatCrunch. This is something that's going to be super important to you moving forward. Calculating the sample variance by hand is something that I'm confident that you can all do. I'm also confident that you can calculate a sample median and a sample average by hand. I'm also telling you that you don't have to. I can show you how to do it in StatCrunch, and you are welcome to do that moving forward. So let's talk about how to do that. If we pull up our Pearson course, your screen doesn't look like this. I went directly into the website. But if you open up your course home from eCampus, you will have MyMathLab. From there, we can open up StatCrunch. I'm going to use a data set from our textbook to do this. We talked in one of the previous lectures how to get some of those visuals. Today, I'm more interested in being able to calculate our measures of center and spread. All right, so I pulled up the Titanic data set because it's super easy to do. Um, and I know what kind of things I'm going to get from it. All right, so very easy to calculate measures of center and spread in StatCrunch. It is very simple. Go to Stat, Summary Stats, Columns. Again, Stat, Summary Stat, Columns. Select on Columns. Suppose I want to know about the year the passengers and crew members were born. So I'm going to select born column because that's going to give me their years born. Here on the right is those variables or variable in this case of interest, and super easy. All I have to do is hit compute. By hitting compute, I get a set of summary statistics that will provide me with the sample size, the mean, the variance, the standard deviation, the standard error, which is something we'll talk about later, the median, the range, the minimum value, the maximum value, quartile 1 and quartile 3. So it doesn't give us the IQR, the interquartile range, but we do have the information to very easily calculate it because we can recall that the interquartile range is just Q3 minus Q1. And now I'm kind of curious. So if I ever make a mistake, like I selected the wrong column, one option, of course, is to hit X and then go back through the summary stats columns. Another option is to select options and select the option that says edit. It'll take you back to the previous screen. So one option with this, there are defaults that come in whenever we're doing the summary statistics, where if you noticed, I had selected the column and just hit compute. If there was something else I wanted, then the defaults, which are the sample size, sample mean, variance, standard deviation, standard error, median, range, minimum, maximum, Q1, Q3, like the IQR, can scroll down and I can add in that I want the IQR, I want the sum, Q3, Q1, max. Notice that if you want to select more than one, you either need to hold down the control button and click or the shift button and click. So just selecting so I can have that IQR in there as well. And I'll leave off standard error because we haven't talked about what that is yet. And let's see, anything else? We can do the mode and a lot of these things like the skewedness measure. We talked about what skewedness looks like from a graphical standpoint. In this course, we are not going to talk about skewedness from a mathematical standpoint. So you're not going to get a formula or anything like that. Same with some of these other options. And because why not? Let's say we also wanted a percentile. So say I wanted to get the 15th percentile and the 45th percentile. I can get that in here, hit compute, and here we are. So still got that IQR. I asked for the summation of all the numbers, meaning they added them all together. The normal, mean, median, mode is now here. There are multiple modes. How disappointing. And then we have the value for the 15th percentile and the 45th percentile. So just some options for you to look at. Let's take a look at do this one more time because I do want to make sure that you know how to do this. So this time we'll take a look at the ages. So once again, we will go to Stat, Summary Stat, Columns. I'm interested in the ages. And I can say I want the sample size, the sample average, variance, standard deviation, I'd also like, oops, let's try that again. Da, 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 da. The median, the range, the minimum, the maximum, Q1, Q3. I don't need the sum, I don't think this time, but I would still like to have the IQR, and I'd be curious to see if there was a mode for ages. Select compute, and I can get sample size, mean, variance, standard deviation, median, range, minimum and maximum values, Q1, Q3, IQR, and the mode. So it looks like the average age of someone on this boat was 22. And by average, I mean the age that occurred the most was someone of 22 years old. Um, in general, the numbers you would need are the default mean, variance, standard deviation, but just in case you ever need to get something else, here's how you calculate it. I highly recommend you use StatCrunch in your homework. It is definitely the way I recommend going about these things. All right, so that does bring us to the end of this lecture. As always, if you have questions, please send me an email.